Okay, I'm back. I speed erased the board and kept only the pleasing version of the bound on the board. So, talking about the probability of a good thing happening, that's more pleasing. This is what it means to be a good thing. And it's at least, it's large. It's at least 1 minus this guy. So we're saying that the probability of a good thing is large. So what does that mean? That means it's saying that E out of G is approximately equal to E in of G, with high probability. Now what we're going to do is mathematically sort of break this down, mathematically massage it into a perhaps more intuitive, more useful form, the form that we will appeal to most of the time. Okay, so, and it's convenient to call this ugly looking thing, let's call that delta. Okay, so mathematically what this is saying is that, with probability at least 1 minus delta. And where's that coming from? So we're talking about a probability, and the probability is at least 1 minus delta. So with probability at least 1 minus delta, this thing holds. So this event is true. So the absolute value of E out of G minus E in of G is at most epsilon. Okay, so with probability at least 1 minus delta, this holds. But that is equivalent to the statement that E out is within epsilon of E in. So E out of G is at most E in of G plus epsilon, and it's at least E in of G minus epsilon. Okay, now this is true. Okay? This is an if and only if. But, in the context of machine learning, in the context of learning, we don't care that we have a lower bound on E out. It doesn't help us so much. What we really care about is using this G outside the data. And so what we really want to know is that E out is small, because that means G is approximately F, and we can go and use it safely outside the data. So even though this is true, we typically ignore this part of the bound. Because it's not that it's not true, it's just that we don't usually care about it. Okay. So with probability at least 1 minus delta, this is true. That's for sure. This implies that. Okay, so with probability at least 1 minus delta, this is true. And now I'm going to massage this, okay, by observing that, here we have epsilon. Okay, I'd like to replace the epsilon with something that involves delta, because we're saying that, delta quantifies the probability. Okay, and I'm also going to show that it quantifies the error in some sense. And we can do that because we define delta in this way. So there's a relationship between delta and epsilon. Okay? So delta is defined as twice the size of the hypothesis set, e to the minus 2 epsilon squared n. Okay, now, we can do some algebra ninja. Okay, so take the 2h to this side, invert it, so that converts the e to the minus to e to the plus, then take the log, divide by 2n, and now I have epsilon squared. If I take the square root, then I have epsilon. So if I do some algebra ninja, what I find out, and you can solve this on your own, you find out that epsilon is equal to the square root. So that's the square here, so that's where the square root comes from. The 2n becomes a 1 over 2n. Okay, and then the e becomes a log. So this is log base e. Okay, and I'll write that as ln just to be explicit. Okay, and then the 2h inverted becomes twice the size of the hypothesis set over delta. Okay. Okay, so now if I plug this definition, this equation for epsilon into here, I end up with the following theorem. And I'm writing it as a theorem, although it was just a massaging of that bound. Theorem. With probability at least 1 minus delta. So with high probability. Okay. E out of G is at most E in of G plus an error bar plus the square root of 1 over 2n, the log of twice the hypothesis set size divided by delta. Okay. So you can think of this as a lasso, okay, that's reining in E out. Okay, and it's saying that E out cannot be too large. Okay, And what is too large? Too large is quantified by this error bar. So you can think of this as an error bar that links E in to E out. So this is an error bar. Okay. And the important terms in this error bar are really N and H. Okay. So typically when we talk machine learning, once and for all you fix delta. In other words, you fix, what with high probability means. What do you want? You want 99.9%, you want 99.99, you want 99.99999. So you'll set delta as some small number. For example, delta is equal to 0.001. Okay. Now, you can set it small and it doesn't affect this bound too much because it's entering as a logarithm. So delta enters as a logarithm. Okay. But it's usually some fixed, high probability tolerance. Okay. And you fix it once and for all and you're done. Okay. The twos, they're there for correctness, but they're not so important. The essential dependence of this error bar is on N and H. So I'll highlight that dependence. So this error bar is essentially order of the square root of log the size of the hypothesis set divided by N. Okay. Those are the important quantities, okay, that govern this error bar. And that's beautiful. So this, is a rock solid theorem. Okay. Does this error bar hold always? No. Okay. So you can't close your eyes and be guaranteed that E out is within this error bar of E in. Okay. And that's the unfortunate thing that we had to give up. There's no guarantee. Okay. But what we have is a high probability guarantee. So you can sort of safely, assume that E out is within this error bar of E in, and most of the time you are correct. Okay. Sometimes it'll be violated. Okay. But you can always choose how often you want to be correct. You can always choose the high probability. And if you choose delta in this way, you're saying that with the chances are 99.9%. You can make it 0.000000001, and then you've got 99.999999999%. So are we happy with that? Yes. I mean, most people would be happy with that. Okay. At least we have got a link, and we have quantified that link. Okay. So once you fix your probability, we have quantified that link. More importantly, we have quantified that link in terms of two sort of, important parameters in the learning problem setup. What are those two important parameters? The two important parameters are the size of the data set and the size of the hypothesis set. Okay. And what do we see that's nice in this error bar? We see that, the size of the hypothesis set can be large, 10 to the 50. Okay. But it's only entering into this error bar through its logarithm. So, if the hypothesis set is of size e to the 50, then this number is just 50. And once n gets much bigger than 50, you're crushing it. So we can tolerate large but finite hypothesis sets with this error bar. Okay. We also see an immediate observation is that, there's sort of a trade-off here in the sense that, as you increase the size of your hypothesis set, this error bar is going to get larger and larger. But as you increase the size of your data set, this hypothesis set, this error bar gets smaller and smaller. Okay. So let me box this. Okay. And so this is the quantification of E out of G approximately equal to E in of G. And we've derived it in the form, in this form where E out is E in plus an error bar. This error bar is very important. Okay, now let's interpret it. Okay, and we'll see all kinds of things that we might have been worried about and wondering where did they go. They're going to pop in very shortly. Okay, so for example, okay, how to choose the size of the hypothesis set. Okay. So now we can address a little bit this issue of, we had to fix the hypothesis set ahead of time. Well, why don't I just fix it to everything? Why don't I choose it as an arbitrarily large, complicated hypothesis set with 10 to the 5 million hypotheses? Okay, so, or e to the 5 million hypotheses, then the logarithm of that becomes 5 million, and you're going to need, 5 million data points in order to bring this error bar to something reasonable and worthwhile. Okay. And so let me show you how that plays off with respect to how this out of sample error is going to behave as compared to the in sample error as you increase the size of the hypothesis set. So let's take a graph. Okay. We're on the x-axis. I'm generically plotting the size of the hypothesis set. Now let's ignore for the fact that, different hypothesis sets can have the same size but be drastically different. Okay. So let's just see what we expect to happen. Okay. So as you increase the size of the hypothesis set, let's look at those various errors. Okay. So let's look at the various errors. So errors. And we've got a bunch of things in this formula. We've got the in-sample error, we've got the out-of-sample error, okay, and we've got this interesting looking error bar. And it depends on the size of the hypothesis set. Now, let's fix the data sets. Let's fix the data set. In particular, let's fix the data set size. And why do we fix the data set size? Because, well, that's the statement of the problem. The client gave you the data. It has 452,000 data points. You're done. That's it. Those are your data points. You can't say, well, please, can I have more? Please, can I have more? Okay, don't be greedy. Okay, the data set is given. It's fixed. Okay, that's the setup. Okay, now, let's think about the in-sample error. Okay. So you've got your data, and you find a separator for your data. Okay. And if I increase the hypothesis set, and this will certainly be the case if I increase the hypothesis set to a superset, but let's just generically think about increasing the size of the hypothesis set. As I add more hypotheses into your hypothesis set, it's more likely that you'll be able to find a G that has a lower in-sample error. Okay. So the typical behavior of the in-sample error as I increase the hypothesis set is, to go down. Certainly should not be going up. Okay. So this is the in-sample error of the final hypothesis. As you increase the hypothesis set, I have more choice. Okay. And, I can pick among a larger set, and I should be able to fit the data. I should be able to get a better looking hypothesis. Okay, now let's look at this error bar. This error bar is exactly the price you're going to pay for that increased choice. So as you increase your choices, okay, you're going to pay a price, and that price comes in the form of this error bar. Okay. Now this error bar is interesting because we said that the two important parameters are the size of the hypothesis set and n, but now n is fixed. So and let's assume that we fix delta, and typically we, don't even bother with delta in these bounds. It's just, it becomes the log of 1 over delta, which is some additional constant. Okay. So this thing is increasing logarithmically in the size of the hypothesis set. Okay. The square root of the logarithm in the size of the hypothesis set. And, the 1 over 2n is a constant now. Okay. So let's call this error bar, omega. Okay, so let's call this error bar omega. So I will say that E out of G is less equal to E in of G plus omega. And, it depends on three things, H, N, and delta. But, let's forget about the dependence on delta. Let's forget about the dependence on N because N is typically fixed. But, sometimes we'll need to remember that this guy is in there. Okay, but it's typically a function. It's an error bar that depends on the size of the hypothesis set, the price we pay for that choice. Okay, you can think of it as a penalty for the complexity or size of H. Okay, so I will call that in that picture the complexity penalty error bar, okay, omega of H. Okay, now it's growing like the square root of the logarithm of the size of H. So it's looking something like this. Okay. Omega of H. Okay. And what is this? This is the complexity penalty. It's the penalty, the price we're paying for having an ever increasing hypothesis set. It's the error bar. It's the error bar for what? It's the error bar that links E in to E out. Not quite. It's the error bar that links E in to an upper bound for E out. So let's look at this upper bound for E out. Now, E in cannot drop below 0. Okay, you cannot make fewer than 0 in sample errors. So this guy is dropping is flattening out. This guy continues to increase. So if I add these two, it's going to increase. Okay, and at the beginning, this guy's dropping fast and this guy's increasing like the logarithm. So you might think that this sum, and this is typically the case, this sum has a behavior that looks like that. Okay. Where at the beginning it's decreasing because your complexity penalty is increasing not too fast, but the in-sample error is increasing very quickly. Sorry, it's decreasing very quickly because you're giving me a little bit more and more choice, and I can choose a much, much better G. But as you give me more and more and more and more choices, diminishing returns with respect to fitting the data, but I'm going to keep paying the square root of log hypothesis set size. I'm going to keep paying that price, if you keep giving me more and more hypotheses to choose from. And so typically you get this U-shaped behavior, but look at what that says. It says that there is an optimal, let's call this hypothesis set size H star. Okay, where you expect this bound, and okay, we will take this bound as a proxy for Eout, even though it's just a bound. Okay, there is an optimal hypothesis set size, okay, which accomplishes the best trade-off between getting the in-sample error low, okay, and not paying too much price for the choice. Okay, you're not paying too much price for the choice. And this optimal hypothesis set size is now going to depend on the specific details of this curve. And now it becomes useful to remember that there's also an n in here. And so depending on the number of data points you have, okay, you can sort of try to identify what the optimal hypothesis set size, if you can sort of understand how this in-sample error is expected to behave. Okay. And the important thing is I don't need to know the specific data. I just need to know how many data points are you going to give me? 400, 4,000, 40,000, 400,000, 4 million, and so on. Okay. This trade-off is fundamental. This trade-off is fundamental. This trade-off. And where's the trade-off? The trade-off is in this blue curve. You can improve your out-of-sample error up to some point, at which point, your out-of-sample error starts increasing. It's a trade-off between the in-sample error and the complexity penalty, the error bar. Okay. The trade-off between the in-sample error and the complexity penalty. And it is fundamental. It is always there. Fundamental. It's always there. Okay. So what does that mean? It means that there is a very serious role for the machine learning expert. Okay. It's not as trivial anymore as just, saying, oh, I've got this, package called neural network. So let me pick the biggest neural network that I can run on my machine and bam, throw it on this data set that you gave me with 4,000 data points and boom, look, I got a beautiful in-sample error. Anyone and their mothers can do that. Okay. But the machine learning expert has to understand that, it's not just about picking the largest, most sophisticated, most complex hypothesis set that's going to fit the data, that's going to look most on the data, that's going to look best on the data, because something much smaller might be the hypothesis set that sort of attains this optimal trade-off, because now we understand that we don't care about E in, we only care about E out. Okay, and E out is only attached to E in via this error bar, and we need to simultaneously optimize both. So there's this trade-off, and it might require us to use a much smaller hypothesis set. Okay, and that's determined by the size of the data set. Okay, and now that I have to use a much smaller hypothesis set, first I recognized that I had to use a much smaller hypothesis set, and second, now I need to really use my expertise to figure out what exactly is that smaller hypothesis set going to be. And let me give you a hint. The perceptron is always a good choice to start off with. That's pretty much the simplest. But it still doesn't fit within our theory because that's an infinite one. It's an infinite hypothesis set, but the idea will remain when we show you the theory for infinite hypothesis sets. It's going to be the same idea. Okay. So, so there's a fundamental question that we need to address. And it's sitting in here. So this is a theorem. The fundamental question is sitting in here, which is that, oh, this is all well and good, Malik, that, you have established now that, E in is approximately equal to E out. Okay? So we have established that E in is approximately, or E out is approximately equal to E in for G. Okay? And that's a great step. It means that after learning with a finite hypothesis set, I can reach from inside the data to make a conclusion about outside the data. So at least I can learn something about what's going on outside the data. But is it enough? Okay? Because this just says that, E out is approximated by E in, whatever E in you see for G. Okay, and if you remember back to the learning problem setup, there was nothing in there which said anything about E in when it came to learning. So what's the definition of learning? The definition of learning is that learning, so this is great that I can reach from inside to outside, but that's not the definition of learning. The definition of learning is that G is approximating F. There's nothing to do with E in. Or in our new language, the definition of learning is that E out of G is approximately equal to 0. Okay. Well, what does that have to do with, E out is approximately equal to E in? Okay. We make this sort of leap now, this beautiful sort of Gedanken moment. Okay. But if I know that E out is approximately equal to E in, and while maintaining that condition, if I can simultaneously get E into 0, then I have learned. Okay. And so now we will introduce you to the two-step approach to learning. So the two-step, we're going to keep this nice thing here, the two-step approach to learning.